Okay, so today we're going to cover lesson 2, electrical potentials difference and electrical current. So these are things that we did cover in grade 9 already. And please make sure you go and watch the video that I assigned before just on the concept and analogy that you can use to understand what potential difference and current is. So the two equations we'll be doing in this lesson is the potential difference equation and the current equation. These are easy if you know the name and the unit for them, because just like something is measured in ohms is important that you know that's resistance. Something that's measured in coulombs is important that you know that that is charge. So I thought that it would be a good idea if you can take the time and copy out the chart, and just so that you know what each stands for. Okay, so the symbol V stands for, it can be called the electrical potential difference. So I'm going to write potential difference. And another commonly used word is voltage. Okay, so those two words are interchangeable. The units that it's measured in is in volts. Okay, capital V. Delta E is change in energy. And just like other energy, it is measured in joules. Capital J. Q is something that is not as commonly seen, but we did use it in grade 9, but I'm just going to quickly tell you what it is again. It is the charge. So electrical charges, and charges is measuring coulombs. Capital C. Okay, so we've covered V, E, and Q. I is current and is measured in amperes with the capital A. And time, delta T, is measured in seconds. So the same SI units as before. So those are the equations that we will be using. Okay, and then we're basically just going to jump ahead to this page. Okay, I did mention this when we were talking about the circuit diagram yesterday, but I just wanted to make sure that you have this highlighted in your note. Okay, to measure electrical potential difference, you use this thing called the voltmeter, and it must be measured in parallel. And yesterday we already drew circuit diagrams. So if I have some sort of battery and a load, and say, for example, if the question, or if you're doing a lab and you're like, oh, please measure the potential difference across a battery. So what you would do is, because it's always measured connected in parallel, and in here it says that it's connected to either side of the device. So you actually have to have 2 points wrapping around the device and hooked up the voltmeter. Okay, you're measuring the potential drop. So you're going to have to measure kind of the difference, what the potential difference is started at, and then what it ended at after it goes through whatever the device is. So you could use it to measure loads or a source. So this one would be measuring the source. But say in the question, say, can you also measure the potential difference of the light bulb? So what you would do is you would, you can like unplug this and then plug it in across the light bulb. Okay, so it's always connected in parallel. And then when they talk about current is basically the rate, okay, how quickly the charges are going. So the bigger the current, the quicker the electrons are flowing. And we use an ammeter to measure it, current, and they have to be connected in series. So what that means is, if I have a circuit, whatever the circuit is, and say they wanted you to measure what is the current going through the light bulb. Okay, so if I have a light bulb and they're like current, you have to, like, if this is the original circuit like that, and they're like, oh, can you plug it in? Too bad that I can't really do a lot with you, but hopefully with the video you can see it better what's going on. What you literally need to do is you need to unhook and actually put a device that is in series to make it one after another. So you actually need to break the circuit, unplug it, connect it up like that, one after another. Okay, so knowing that it has to be connected in series, so one single path for that. Okay, so let's go through examples. I missed the example right here. Calculate potential difference. Sorry, though, this will be the last page. Calculate the potential difference between the negative and positive terminal of a battery is 1500 joules of electrical potential energy is transformed to move 125 coulombs of charges. You will find the chart useful to tell you what symbol is what. So knowing the name electrical potential difference, I want to calculate what is the electrical potential difference, meaning your voltage is V. And then they tell you that it's measured in joules, so you know that this is the energy. Even without reading the words, the unit can help you recognize what symbol they are talking about. So 1500 joules. And then they tell you that it moved 125 coulombs. So if you go back to the chart we were doing, 125 coulombs, what's measured in coulombs? Coulombs is measuring charge, which is Q. So they also gave you Q is 125 coulombs. And do the calculation. So delta E, sorry I missed the delta, the change in it, over Q. So 1500 divided by 125. So I got something like a 12. So 2 sig is good. So 12 volts. So you need to go back to the chart, right? Oh, V is measured in volts, capital V. So that's the unit of my answer. Okay. So now doing the second question. I'm jumping all over the place, but I'm just going to finish the math first. Question 2. I'm at the last page, the last example. Calculate the amount of current through a wire that is 0.85 coulombs passes a point in 2.5 minutes. So they want you to find current. You check up, current is the symbol of I. And they give you 0.85 coulomb, which is your charge, Q. And the time is 2.5 minutes. And we know that it has to be in SI unit. So 2.5 minutes, 60 seconds in a minute, so 150 seconds. So everything is in SI, is good to go. Equation is I equals Q over delta T. So 0.85 divided by 150. 0.0057. So 2 significant digits, 0.0057 is what I'm going to write. The answer is in amperes because it is current. Okay, then there's two more information about electric current. Our nerve cells can create really little bit of it, and if it's too much, it can hurt our body. So I just wanted to tell this story very quickly. I don't want to waste your time. I have a picture of Nathan's hand, my son, Nathan. Okay, this was grade 3. And he found a paperclip on the ground. And he thought that, wouldn't it be cool if I hold on to the paperclip and I poke it into an electrical outlet? So, yes. So he poked it into the electrical outlet. And it wasn't too bad. So you saw what it looked like. But on the phone call from the vice principal, Nathan has put in a paperclip and he pushed it into the electrical outlet. His finger got split open. So that was the message that we got. So I understand what it means by it got split open now that we've seen it. But when we first heard it, we thought that it was, you know those things called the cheese string? You know that guy with the hair that's all like into different strands and stuff? I was thinking that his finger was split open like that. But anyway, he didn't get shock. He got burned because this is a short circuit. Okay? So he actually got it, the paperclip just got really heated up. And yes, and there are protection at home that they would actually short the circuit and actually would stop the flow. You have to go to the circuit breaker and reload it again. But anyway, so that's what happened to my son when he was in grade 3. So you couldn't live up to his story because he's now in grade 9, and then there are these people that he went to school together when he was grade 3 because he went to the gifted program. In grade 4. So he hadn't seen these people. And then in grade 9, they're in the same school again. It's like, oh yeah, I remember you. I remember Nathan. You're the one who who put that paperclip in there. And then also Naomi was also burdened by it because when his grade 3 teachers was also Naomi's grade 3 teachers. And so every time when Naomi raised her hand to try anything, it's like, yeah, I just hope that you're not like your brother. You wouldn't do it and you wouldn't be too gutsy to do something like that. But anyway, that's my story. I do miss telling you guys story. Hopefully this brightened up your day. His finger didn't really split open like it was told. And he just got a minor burn. And basically that next 2 day his finger was wrapped up in like super big white gauze, and then he just kept holding on to the ice, like a couple of pieces of ice, and just keeps it cool, and it was fine in a couple of days. But anyway, do your homework, and then the next. Okay, sorry, I lied. I said I was done, but there was one important concept that is important for tomorrow's lesson, so I need you to pay attention to this. So we're going back to the potential difference. Very important thing that you need to know is that at a source, you will have an increase in electrical potential. And at a load, you would have a decrease in electrical potential. Okay, so if I have a battery and if I have, say, different loads. So hopefully you remember sources are like battery, power supply, AC outlet right from the wall. Loads are things that uses it up. So a light bulb, a motor, and the resistors are the load. And what they're telling you is that you need to know that every time at a battery, your voltage will increase. Okay? And every time at load, your voltage will decrease. Okay? And if I actually move ahead, basically, there is this law that's saying that if I am an electron leaves from the negative and it goes around in a loop, that the total energy increasing, the total potential that increases have to equal to the total potentials that are dropping. So I'm just going to totally move ahead. If I tell you that if I have a battery, you know how your battery has like that little number written on it. If I have like a AA battery and I tell you that this AA battery is a 1.5 volt, and I'm telling you that there is this guy that is equals to 1 volt, and I'm asking you, what do you think the potential difference is for this guy? Okay, the rule that says total increase equals to the total decrease. I'm going to stop talking. You're going to tell me what the answer is, but tomorrow we'll